Hey everyone, I'm Nick, and I'm one of the co-founders of Helios. Helios is a developer platform and RPC provider for Solana.
My name is Swen, co-founder at Light Protocol, and Light is a protocol for scaling Solana with ZK.
So you might be wondering why are two different businesses here right now, and we basically partnered to build an end-to-end scaling solution for Solana. Today we're going to talk about ZK compression, what it is, how it works, and most importantly, why it matters. We'll do some demos, and we'll also go and have a Q&A at the end if you have any questions.
Awesome. So first question, what is ZK compression? Now, to understand that answer, we'll provide a little bit of context first, and then we'll just recursively go deeper over time. And by the end of the talk, hopefully you'll all understand what ZK compression is. First thing to know about Solana is that compute on Solana is very cheap. But actually, data storage is very expensive. So if you want to create 1,000 token accounts, that costs you $300. Now, the thing is, if you want to scale your application, right, you have an application, you hit a lot of users, that cost becomes really basically economically prohibitive for you. If you want to create 1 million token accounts, that's $1,000. And so that cost just goes up with the price of Sol as well. So that's a big problem, number one. Now, there's a second problem, which is the state growth problem, which all stateful blockchains have. The thing about Solana is that it has a lot of accounts, right? So the concept here is that if we store data, we store it in accounts. And when we create an account, we have to pay for rent. And rent is expensive. And still, there are 500 million accounts on Solana right now in the total state. And this number is growing. So each day we have like net new, we add about 1 million new accounts per day. Now, those are two major problems, and ZK compression basically fixes this. We have, on one hand, 1,000 times cheaper accounts for Solana. Then we have a solution for state growth, which is ZK compression. And then lastly, this is a little bit of a side note, we'll get to it at the end of the talk, is ZK compression is also a foundation for ZK compute on Solana. All right, just to hammer it in once more, we have 1,000 times cheaper accounts, we have a solution to state growth, and we have a foundation for ZK compute on Solana now. All right, so if we take the words ZK compression, what does it actually mean, right? So we have state compression on one hand, then we add ZK, zero knowledge, to it. So let's first look at state compression. It's basically 4 major points at the high level. First point is, what we do is we take millions of accounts on Solana, and we compress them, we hash them together into one small fingerprint. Then we take that fingerprint and we store the fingerprint in an on-chain account, and we store the actual underlying account data off-chain, for instance, on the Solana ledger. Now, lastly, we have a proof mechanism that lets us verify on-chain the validity of these underlying off-chain accounts using the fingerprint that we stored on-chain. So that is sort of the high level of what state compression is. And then ZK compression is just using zero-knowledge proofs, SNUCs, for the last element, which is the proving part.
Yeah, and so now we'll talk about why ZK compression is the right solution as a state compression kind of primitive. And what I'm going to do is outline the key features that essentially make it the right solution. So first off, what I really want to hammer in is that compressed accounts are essentially analogous to regular Solana accounts. They are very, very similar, which means that you can apply the same sort of Solana development techniques that you do today with the ZK compression system. It'll feel the exact same, which means the barrier to entry for developers is very low. And it just essentially will make this whole system easier for you to get started with. If you look at for example, the API that the indexer exposes, which we'll talk about more in the future, you can actually just see how similar it is. You can see that, for example, get account info just maps to get compressed account. And this sort of like one-to-one mapping continues for essentially the whole RPC API. Now, another really important point that we want to hammer in is that compressed PDAs are supported. So PDA is a program-derived address, and essentially what this is it's a deterministic address. It's a way that given a certain program plus a seed, you're able to get consistently the same account out of that. Now, this is actually so important that we decided to rebuild the entire compression system into ZK compression for this very reason. And it's powered under the hood by the ZK, which is a bit out of scope of this talk, but essentially it's the reason why we did all of it. And the way that compressed PDAs work is that basically you take the program ID and say you have a domain name service, like a DNS, and you want to take that key, you can then map that to one single account every single time, which means you don't have to worry about having race conditions or collisions and accidentally creating two DNS value accounts for the same key. This is a super powerful concept that if you've done any Solana development or if you've done just development in general, you'll understand how this is like a basic primitive that needs to exist in any system, and it's fully supported with ZK compression. So if you think about where this will take Solana, what I want to emphasize is that because it has PDAs and because there's also this ability to compose programs together, is you're able to have these sort of more complex architectures. You have multiple programs, different PDAs, the sort of development experience you're used to building, the applications you're used to building on Solana, but you're going to be able to do this with 1,000 times less cost for your accounts. That is huge. This will open up use cases that we probably haven't seen before because people were essentially just priced out of it. So there's a few things I really want to hammer in here that are quite important. First off, everything is executed on Solana. It's not an L2, it's not a Validium. Essentially, you have the data availability automatically through the Solana ledger. Because it's executed on Solana, it means that it's verifiable, and it also means that it's fully composable. Now, for those of you that are familiar with the old compression system, I just want to make a quick little call out that one improvement we've done here is that the zero-knowledge proofs have this feature where they shrink the proof sizes down to a consistent 128 bytes. What that means is you now have a lot more room in each transaction for essentially just whatever else you need to do, which means easier composability and just more room for activities. There we go. Another important feature is decompression. This is really important because it essentially prevents lock-in and allows for simple interoperability. Any Solana account today, or in general, can be compressed. And when you do that, you get the rent cost back. You can also take any compressed account and decompress it, and you obviously need to put your rent payment in there. So that means you can go between the two. So if you ever have a compressed program, say a compressed token, and need to decompress it, you can then decompress it and feed it into, say, like Jupyter and do a swap or whatnot. It also allows for a sort of back and forth between hot and cold state. So you're actually able to, say you want to create like a video game where you have, say, a bunch of different cards and items that are all compressed. You can decompress those when you go into a battle, have quickly iterating state, and then you can compress it afterwards, saving the final result, say like the hit points change and whatnot. So again, very sort of powerful concept. The other thing, too, is I want to emphasize this is a fully generalized solution. It's not tied to a single program or business logic or application. It is essentially just Solana accounts and compressed with low cost. You can do anything you want to do today. It has out-of-the-box indexing support. It's fully open source, production ready. And yeah, that's pretty much the main point I want to make there. But going even further, we've also added, just in the first release, compressed tokens. And we built compressed tokens using the exact same tools you would build to build any application that leverages compression. It's no different. And so you obviously get the 1,000 times cost savings, but you also, I suppose what I want to say is that the compressed token program we've built mirrors the Solana token program pretty much one-to-one, which means it feels the exact same to work with. We're also going to include token extensions, which will be live at the beginning of 2025. And as I mentioned before, you get all these other benefits like decompression. So you can airdrop tons of tokens and then decompress them if you want to use them in, say, DeFi. So now we're just going to do a demo so you can actually see how it works and just see how, how essentially it mirrors the Solana experience pretty much one-to-one. And so what we're going to do here is we essentially have we're doing this all locally, and we have a test validator similar to the Solana test validator. And we're going to go and essentially create a token and mint some tokens.
So that's what we do here. And one thing I want to highlight here is that ZK is thought of as like this holy grail of like, very expensive computation. But what you see here is that actually the transfer, and we'll do it right here, looks a lot like a regular SPL token transfer. And that is because we've shrunk down the proving time to like milliseconds. And so we think that's pretty cool because it's like a production-grade consumer ZK right there for decreasing costs of token accounts. And so what we have here is we have 42 minted token accounts in compressed form. And now we transfer 12 of them to another person. And we see that it takes, right there, we see that it takes like, similar to a regular Solana transaction. And then we check the balance and we see that indeed we have sent 12 tokens, compressed tokens, to another person. Awesome. So this demo looks cool, but how does it actually work under the hood? Now, to recap, you know this slide. We have these 4 points at a high level about what state compression is, right? So to recap, we have millions of accounts. We fingerprint them. We hash them together. We store the fingerprint on-chain. We store the underlying account data off-chain, for instance, on the Solana ledger, which has the same safety guarantees as Solana itself. We use on-chain accounts. And then lastly, we have a proof mechanism that allows us to, in a smart contract, verify this off-chain data on-chain. Now, if you dig deeper, there are 5 major components in the overall system. And I'll just walk you guys through it. So the first thing that is very critical to understand is the concept of state Merkle trees. And we call it the forest of state Merkle trees. And I'll get into why it is a forest in a minute. But basically, this concept helps us understand how we create this fingerprint that I mentioned earlier. So say we have 4 accounts. What we can do is we can hash them, and then we can recursively hash them together into this upside-down tree structure. And this is what's called a Merkle tree. Now, the root on the top, so this hash, the final hash on top, is a 32-byte hash. Now, basically what this does is it gives us a cryptographic guarantee about the underlying account data of all the different accounts. And what that means is that it ensures integrity. So it's really easy for us to verify that a given account state is actually part of this Merkle tree by verifying it against the state root. Now, there are 2 relevant programs here in the protocol. There's the Light system program, which is sort of an on-chain VM, and it mirrors the Solana system program. So all it does really is it writes to the Merkle tree. It enforces the generic account model that Solana also does have. And then it also deals with verifying the uniqueness of PDAs. Next up, we have the compressed token program. And as Nick already mentioned, compressed token program mimics the SPL token program. So what it does is it just enforces the SPL data layout on top of the account model that we have for compression. Now, there's one other important concept that I want to highlight here in this section, and that is the concept of the forest of state Merkle trees. Well, there's some nuances there, and that's why we have forester nodes. So in short, foresters manage the light forest. And what that means is, when we look at the compressed state changes, what actually happens when you update a compressed account is that you actually add a new account state to the tree, you append it, and then you zero out or nullify the old state. There are 2 implications of this. One implication is, well, whenever there's a state update, the root changes, right? Because the state underlying it changes, and therefore the root must change as well. The changes trickle up the upside-down tree. Now, there's a second facet to this, which is, well, the trees fill up over time. Eventually, they get full. And so that's where the forest of light trees comes in. Forester nodes basically maintain the state root, so they update the state root in sort of an asynchronous process. And then they also roll over full state trees. Now, I should note that for your own state trees, running your own forester node is permissionless. And lastly, we have the indexer.
Yeah, so I'd like to next introduce Photon. And essentially, it's the open source indexer for ZK compression. The purpose of the indexer essentially is to listen to what's happening on the chain with respect to compressed accounts getting updated, created, mutated, et cetera. And essentially, it is caching the current state. And it's also responsible for generating the proofs that you can then use to verify the data or to also mutate the data if you so choose. So in terms of features, it's fully open source and it's production ready. And we've intentionally tried to make some improvements and take the learnings we've had from working with the first variant of compression to make this indexer much easier for everyone to use, regardless of whether you're an individual developer or if you're an enterprise or RPC provider. First off, local development is far easier. You have a CLI, it's like a one-click thing where you just run it, and it'll automatically work with your local development. We also have an explorer that works locally, so it's more of a dev-focused explorer, so you can kind of see your compressed accounts visually and understand what's happening, look at the transaction history, et cetera. Next, I want to talk about something important, which is snapshot support. It will generate snapshots at a daily period, which is really important because it allows anyone else to start the Photon indexer from a snapshot, and they no longer need to go and re-index from Genesis, which means your boot times and start times are a lot faster. And as you can see here, we are able to catch up in about 15 minutes or less. Also, the advantage of having snapshots is it increases your sort of replication factor or your sort of, yeah, I guess your replication factor. It's like it makes it easier for anyone to run it because if, say, any RPC provider stops wanting to offer support for compression, you just need to go grab that snapshot and you can run it yourself. There's no real risk anymore because we can offer these snapshots and store them on somewhere decentralized like Filecoin. And lastly, I want to just point out that, I guess I've already mentioned this, but it really is built for everything from individuals to enterprises. So if you want to index your own data, you can run Photon, so it's only indexing a subset of the data. It means you need much lower hardware requirements, smaller database, et cetera. You can run it with SQLite in one CLI command. Or if you want to index everything as an RPC provider, it also, of course, facilitates that. So how to use it? Well, it's available today on any Helios plan. You can also, as I said, run it yourself. Or you can just talk to your other RPC provider and just ask them to start offering it. Awesome.
So one other major thing to highlight is developers. We are focused on developers. And so there's three major things that we've built and that we're building out and improving on. And the first thing is the SDK, which is like Web3.js, if you use Solana Web3.js, but for compression. So what that means is, if you have your compressed token transfer, all you need to do is you need to first fetch your compressed token accounts. Then you can use those token accounts to fetch a validity proof from your RPC or a dedicated prover node. And then lastly, you can just build your instruction like you would with the SPL token program. So you build the instruction, you tell it what you want to send, how much, which mint, right, and to whom. And then you can go off and build your regular Solana transaction. All right, the second thing is, you saw it in a demo as well in the beginning, and Nick highlighted it, which is the full local development setup. So we have this test validator that comes pre-initialized with all you need for local development. So this is all the programs. The Photon indexer runs locally. The prover node runs locally. So you have all of that ready to go. And then lastly, Anchor macros. So if you are into Solana program development, you've probably heard of and used Anchor. And basically, our goal is to make developing with compressed accounts feel exactly the same as developing with regular accounts. So this is what this looks like. If you have written an Anchor program, you will feel the similarities. All right.
So next I want to talk about Airship. This is something we built to essentially let people start using ZK compression today for users, essentially. And what it is it is a mass airdrop token. Essentially, it's very easy and cheap to use, and you have either a UI you can use or a CLI. And everything's open source, so you can go use it. You can fork it if you want and make changes as you need. But essentially, what I want to point out, I guess, is that in the best case, you airdrop these compressed tokens, and over time, the ecosystem starts using compressed tokens, for all sorts of different applications. But say you just want to immediately convert that, you can't. You can just decompress it right away, and we've also built that into the UI. So essentially, like your worst case is that using Airship would basically be a pre-built airdrop tool that you could use, and it just will be the same as using normal tokens. The other thing I want to point out is that it automatically supports airdropping to Solana mobile holders. It can also airdrop to any token, so holders of a certain token, or an NFT collection, and you can also provide your own CSV if you have a pre-generated list of users you want to airdrop to. Probably the easiest way to go over it is just to show a demo. And in this demo, what we're going to do, we're going to use the UI. And we're going to use a CSV in this case. And then once you import that, you're going to go and specify the token you want to airdrop and the amount, confirm everything, and then you can run it. Now, one thing that's nice, too, is that both the CLI and the UI, if, say, you lose internet connectivity or something goes wrong, you can resume your airdrop from wherever it is midway through. It keeps track of that state, which is quite nice, because some of these airdrops might take a little longer, like 30 minutes or 45 minutes, if you're doing a lot.
All right, so the TLDR, ZK compression scaled Solana, and we hope that you've all now sort of gotten a glance and sort of a high-level overview of how exactly it scales Solana. But then there's, that's basically cheaper accounts, right? And then solving the state growth problem. And one note on this is basically the state growth problem, right? The way that ZK compression solves this, or gives a solution to solve it, is that you basically only store the final root hash of all the accounts in the active validator memory, right? So that's effectively how we approach the state growth problem. Now, there's these two scaling problems that ZK compression solves, but ultimately what ZK compression does is we think it's creating a new design space for apps. And there's two types of apps, basically. And we have listed a bunch of ideas on the next slide. And there's two segments. So one is just like dealing with cheaper state. So I'll just run through a list, and there's a lot more that we've seen people do and that we like to see play out. We have SBL token compressors, 1 billion meme coins. I think that's an interesting one. And then prediction markets for Twitter posts. You could also use state compression with ZK to create identifier PDAs for deepen networks, where you basically register your different nodes on-chain. And then there's the second section, which goes into the ZK part and into the verifiable compute part. And three things I want to highlight here that I find very interesting are verifiable reward calculations. So you have some sort of like verifiable off-chain compute. Just in the previous talk, you've heard about Bonsol. That's one approach to do it. And then you could plug into and actually write that data to the Merkle tree roots that ZK compression maintains. Now, there are two other ideas. For instance, trust minimized bridges, where you basically sync Merkle roots again. And then ZK identity protocols. I think that's also something that's pretty interesting. So there's a bunch of these ideas. We have a lot more out there in the documentation as well. But yeah, this should just give you sort of a sense of like how broad the applications are for ZK compression.
So this is live on mainnet today. So there's nothing stopping you from getting started. We have the docs, we have demos, everything to start. There's also DevNet, LocalNet, testnet support, whatever you need. We also are hosting a hackathon. You still have time. There's up to $45,000 in prizes. And also, I guess, as we wrap up, I also want to give a special thanks to all the people who are behind this project. We have Pedro, Kuhn, who worked on the Helios side, and then we have Yorit, Michael, Sergey, and Tilo from the Light Protocol core team. And we have about 5 minutes left, so we can run through a Q&A if anyone has some questions. Awesome. And I believe we will have some staff out here who have mics that they can give to the people who have questions. If that doesn't work out, then I'll just go around and ask directly. All right, seems
Do we have
like
people
no
with mics?
staff. Does anyone have questions? You can raise your hands. I'll just go around then. OK, yeah, let's start here. Sure. So the question is, what's the incentive to run the Forester nodes? You can take that one.
Yeah, so running a Forester node, the way that we see it, it's very similar to like running RPCs, right? And running photon indexers, is that when you care about your own compressed state as an app developer, you have an incentive, natural incentive, to make sure that your state trees are being maintained. And so you have an incentive to either run a node yourself if you want to self-host, or you could pay another provider for it.
Awesome. Anyone else? Maybe over here? I can jump down. And the gray shirt. Oh, we got a mic? Awesome. Yeah, that'll be great.
Okay, so when you're compressing states, what's the difference with the existing state compression program, like on the SPL library? And another question is like, your token program created by you, is that supported by any like exchanges? So creating tokens in your token programs does not compatible with the existing ecosystem. How do you fix that?
Okay, yeah, I'll start with the second question, which is essentially, if I get it correctly, you're asking, is the compressed tokens, are they compatible with exchanges and DeFi? And if not, how do you rectify that? So essentially, the answer is sort of yes and no. They're not directly compatible because they need to actually support them, which they can do, but you can decompress them. So if you have a compressed token, you want to decompress it, you can convert it into a normal token, regular SPL token, and then you can use it in DeFi the exact way you normally would. So there's no real lock-in, but we do hope that basically because you get to keep the cost savings if you don't decompress, and it is very easy to use, that we'll see more and more people basically building applications that leverage the actual compressed state. Now, I guess while we're here, I will mention that if you want to do rapid fire trading or something, like decompressing is a better way to go. Compressed state is best for cold applications, and regular accounts are good for hot state. And that's kind of one of the big important things with this whole system is that we have that state growth problem, right? So essentially, there's tons of state there that is just cold. And now we're going to be able to move that to a compressed state, which has all the benefits we talked about. Awesome. Any other questions?
I think there was another question as well asked by
the first part?
Yeah, so to repeat it, I guess the question was around why don't we just use the regular SPL account compression program and what it changes. And Nick has highlighted this in the beginning of his slides. There's a couple of improvements that we've made and where we basically figure out we have to rebuild this from scratch. And this includes the support for PDAs, right? So like what that actually means is like proving not only that your state is part of a Merkle tree like inclusion, but also being able to prove in an efficient way, so like within the transaction size limit basically, that a given address is unique. So what that means is that you have something that's called an address tree. And this address tree is very similar to a state Merkle tree, but with one nuance. What you actually do is, by proving inclusion in a leaf, you prove exclusion of a certain range of numbers, right? And so what you can do is, you can actually display or handle the whole address space. In our case, it's 248-bit address space within much smaller Merkle trees. And so that's how you get the uniqueness property. And this is something that we added, that we basically had to rebuild from scratch. And then I guess the fundamental difference as well is we're using zero-knowledge proofs, snarks, to keep the proof size consistent, independent of how many accounts you want to update, read or write in one transaction, and then how many inclusions or exclusions you want to prove. And this is very important because Solana transactions are very small by nature, so like 1.2 kilobyte. And the way to achieve these like fast proving times to generate these proofs, you have to actually use a different hash function for these state Merkle trees. And so therefore we couldn't use the original SPL account compression program and then build our system program and compressed token program on top of that.
Sure. I think we have time for one more quick question, if anyone else has one. In the back there?
Are there any limitations around the concurrency that's happening inside a single tree during a slot?
Don't take that one?
Sure. So the question is, what are the limitations with regards to concurrency when using compressed accounts? And Nick mentioned it in his one answer, which is that if you have account updates to the same account, like you write to that same account many times in a block, you should not use the compression for that. What you can do is you can just keep that specific account permanently decompressed as a regular on-chain account. For instance, if you have an AMM pool account, you want to keep that one decompressed, right? And then basically all the other state that is colder than this like hot account it's designed. The system is designed in a way where you can then interact with these decompressed accounts and mix and match within one transaction.
Thanks.
Yeah. Awesome. I think that puts us at the end of time, so we'll wrap up here. But thanks for the questions, and yeah, thank you everyone for having us. Okay.
All right, cool.
Keep the applause going, keep it going, and welcome to the stage, Jacob from Risk Zero.
Nice to see everyone. Excited to continue to expand on the ZK stuff going on in Solana. So the title of the talk is Boundless Execution on Solana. First of all, let's do a little bit of a history recap. In general, right, blockchains are kind of in this dilemma of security, throughput, and decentralization, and everyone kind of make trade-offs, right? So you can have higher hardware requirements, more or less node operators, different sort of execution limits, and different sort of block frequencies. In general, when you think of execution on a blockchain, you're constrained by the smallest node. Why? Because that person has to keep up, continue to execute transactions. With ZK, we get boundless execution. Instead of being restricted by the smallest node, we become a sum of them all. With ZK, you can have really brief verification that someone's done an execution correctly. So if someone wants to generate, has 30K GPUs, they can do 30,000 GPUs worth of verifiable execution. If someone has 100, then you can do 100. So you kind of get this really nice property that you can just do a lot more execution. Let's do a really brief history of ZK. In general, I think ZK has been talked about this holy grail technology more on the Ethereum ecosystem side since 2015, 2016. I think it's kind of obvious that there's not many applications live today. Real quick, just mention here, when people mention ZK normally, they're normally talking about verifiable compute. That's the syncness re-verification factor of it. You can add privacy on top as well. So why are there no ZK applications, right? Well, ZK is a little bit broken. Performance has not been there, but there's been a lot of research around it. It's been inaccessible. The example I always give is currently you have to write these ZK circuits. Most of you can probably code the game of chess in a high-level language. If I asked you to code the game of chess represented by polynomials, probably less accessible. And then there's also an ongoing maintenance and security issue. If you ever need to change your ZK program, you normally have to change a large portion of your program. These circuits are also really hard to, one, audit and make secure in the first place. So Risk Zero fixes ZK development. All you need to know about this is we essentially made a ZK circuit that looks like a CPU. We can take Rust code, compile it down to a RISC-V binary, and generate a proof that this code has been executed correctly. So what does this mean for a developer, right? It becomes really usable, okay? So you just write programs in Rust. You can use 70% of the most popular Rust kits inside the ZK VM. Your development time is 1,000 less. You don't have to worry about this, the security as much and the maintainability. If you want to change your program, you just change a line of Rust and you're getting it going. You don't have to get your circuits audited. And then you get this boundless proof part of it. We have this other innovation called continuations. We can kind of just generate proofs for infinity. So we kind of stitch them on the back of each other. So let's talk, right? Why should a developer care about becoming boundless? I'm going to share some examples that are all being worked on today by partners. First, you get boundless skeuomorphic execution. Today, execution in ZK is cheaper than anything on chain. We can verify a DEX swap for 1/10 of a cent inside the ZK VM. So we have like roll-ups. There's some people on Solana looking to do it using our ZK from network extensions, co-processors. Unfortunately, this video is not loading. We actually ran the original version of Doom inside the ZK VM with rendering. And there's the picture now. Next, you could do some lot more like complex trading strategies. We have one partner, not specifically Tokamak, but you could track a moving price average over a month across multiple assets, across multiple chains, doing way more expressive things. And lastly, we can start to bring in Web 2 infrastructure on chain. So here's a good example. We can do sort of ZK login with a Gmail. We generate a proof that you actually own a JWT token. We can also do this with OAuth tokens, Twitter logins. You can find this example on our website. Yeah. So if you would like to figure out more, risk zero is, you can find all the ZKVM documentation on the left. And then we're building a protocol. We're calling it the verifiable compute layer. It lets any chain elastically demand on execution. You can think of it a lot, how Chainlink brought price feeds to every chain. We're gonna bring ZK to every ecosystem. Yep. Perfect. Thanks, guys.